Hello everyone. In this video, I will introduce how I conduct automated integration testing for the exchange system. In financial systems, correctness and invariability are the most important factors, especially in an exchange when the matching engine and settlement involve orders and positions. There are numerous scenarios that need to be tested. So in this situation, manual testing just isn't practical because we make a lot of changes and the order placement and settlement process is the main workflow, our most important core process. We can't manually cover all scenarios every time there is a change because there could be 2 to the power of 3 or 2 to the power of 4 such trading processes around 8 to 16 scenarios. Therefore, we must design an automated integration testing system. So when do we use integration testing? It's because the entire system is a distributed architecture, and unit tests cannot cover the entire end-to-end scenario. In this context, automated integration testing is more valuable. Okay, let me first introduce. I'll first introduce our main process, the variables and dimensions during order placement, so you know which scenarios we need to test. First, after a user places an order and sets the price and quantity, the result could be opening a position, closing a position, terminating a position, or opening a reverse position. It could also be after opening a reverse position, then after opening a reverse position, a resource contention occurs. This is one dimension where there are 4 possible positions after an order is placed. The second dimension is after placing an order and matching a deal, the user could be a taker or a maker. Thus, in the taker-maker part, whether they are the order placer or holder, there's a dimension that needs to be covered. Okay, that's 2 dimensions. The third dimension is whether the user is buying or selling. For selling, it includes the recent position changes and the taker-maker parts, which also need to be covered again. So that's 3 dimensions. Finally, there's the order quantity. For example, they may place an order for 5 units and the counterparty might take it in several batches, whereas previous scenarios might involve placing an order for 5 units and the counterparty also taking exactly 5 units, a scenario where it matches perfectly. In this dimension, if we place an order for 5 units, the counterpart might break it into several orders to take them. This is another dimension. So that's 4 dimensions already. If we want to be more detailed, there's a 5th dimension, which is the price, allowing for different order price scenario coverage. In total, there are 5 dimensions. Now let's look at specific test cases. I created these test cases simply using Markdown without making mind maps, because the meaning is the same. In these test cases, we create 3 accounts, A, B, and C. After depositing a certain amount into each account, we begin verifying different scenarios. What is the first scenario? The first scenario mainly tests the position status of A when in a long position. It covers the correctness of all types of position operations, including opening, reducing, increasing, closing positions, as well as flip and concurrent flip scenarios. So how do we test it? In these transactions, A will always be the maker, the one placing the order. After A places an order, B immediately places an order to complete the transaction, with B taking the order. After each transaction, we verify the position and account status. Let's first look at the 4 basics: opening, reducing, increasing, and closing positions. Initially, A has no position, the position is 0, with no contracts. Then he places an order for 5 units at a price of 100. Then B immediately places a counter order to sell 5 units at 100, completing the transaction. So the result we observe is that A's position status is a long position of 5 lots. Then we look at the various fields of the position, such as cumulative profit and loss fees in those fields. Also, we compare the amounts of the main position margin and the spot account on the account, as well as the fees, to verify the status of the position and the account and the result. This is to verify that his opening of the position is correct. Okay, after testing, it's currently a long position of 5 lots. The next step is to test selling 3 lots, which means now it's a long position of 5 and selling 3 lots, equating to closing 3 lots. In the scenario of closing a position, B immediately trades with the counterparty. Then we verify the status of the position and the account. Okay, now having closed 3 lots, A's current position status is a long position of 2 lots. Then A buys 2 more lots to increase the position. Increasing the position by 2 lots, the expected result would be a long position of 4 lots. And similarly, verifying the status of the position and the account. Okay, and then finally, he sells 4 lots to verify, covering the test of complete position closing. After testing, the expected position is completely closed. Similarly, verifying various statuses of the position and the account, the next thing to test is the flip situation. This involves distributed transaction concurrency conflicts and contention handling, so it's the focus of this test. For the detailed explanation of the distributed transaction process, it has been mentioned in other videos. Please take a look at those videos if you need more information. Okay, let me do a simple review here. Our system uses one-way positions. One-way position means the user can only have either a long position or a short position at any given time, not both. They can only have one, their status will only be one. If it's a long position, placing a buy order will open the position. If placing a sell order, it will close the position. If the position status is a short position, placing a sell order will open a new position, and placing a buy order will close the position. Okay, in the flip situation, suppose the user currently has 10 long positions. If he sells 15 lots and they are traded during settlement, it first closes 10 lots, then automatically reverses to open 5 lots. And then both the position and the settlement of these 2 transactions need to be handled. Yes, and this is the basic flip situation. Okay, next is the scenario of flips concurrency conflict involving resource contention. What does this mean? Suppose the user currently has a short position, 10 lots. Now the user places a close order for 5 lots. After placing the order before it's traded, since it's a close position, resources will be pre-frozen. Okay, at this time, if the user has another order, say, if he places an order to buy 15 lots, for example, it will first close the short position and then open a long position if the order is filled. Buying 15 lots, the 5 lots to be closed, have frozen resources but haven't been traded, currently pending. But what about this order for 15 lots? If it trades first, how should it be settled? Since 5 lots are already frozen for closing, how should he handle the closing? Our system is designed this way. It will take over these 5 orders to close the position. After taking over these 5 lots to close the position, it will then reverse and open 5 lots in the opposite direction, and with that, this settlement is completed. If this order trades later, how should it be handled? If it trades later, it will be considered as closed position turning to open position, meaning the position is closed, but it's no longer available. During settlement of the closed position, it's found that his position status has changed to a long position of 5 lots. So this closed position, since he ordered a buy, is considered as a buy. It automatically turns from closed to open position, closed position turning to open. And the settlement result should be that the final position status is a long position of 10 lots. Okay, that's basically what it means. If this part is unclear, review it again for better understanding. This is the second part we need to test, the concurrent trading test. Then the third flip test is actually the same as this one, but it covers an additional scenario. Okay, let's look at how I specifically designed these three scenarios. At this point, we have completely closed the position, and A's account status is that there are no positions. So here I let A buy 5 units with B as the counterparty to facilitate the trade, making A's account status 5 long positions. And then at this point, A sells 10 units, achieving the effect of closing the position and then opening a reverse position. At this point, counterparty B sequentially trades 5 units, and then C trades another 5 units. Then, when observing the results of the positions, we want to ensure they are correctly reversed, from holding 5 long contracts to opening 5 contracts in the opposite direction, and then verify the accounts, all transaction flows, and position statuses. This is the basic flip test. The second test involves designing a scenario related to position freezing and resource contention, which involves concurrent processing. Okay, here, A is in a position of 5 short units. At this point, we let A place 2 orders simultaneously, one to buy 3 units. To close out, this time we close 3 contracts. Out of the 5 contracts, freeze 3 first, and then place another order to buy 10 contracts. To facilitate closing the position and then opening a reverse position. Then we set the 3 units at $100, but don't execute the trade yet. We let the trade of 10 units at $101 execute first. So at this point, B will place an order for 13 contracts, causing the trade to be executed. Our expected result is that the 5 short units will be closed first, and after completely closing the position, it will open a reverse position, changing to 5 long units. Then, B's account executes the trade, freezing 3 units. These 3 contracts are expected to convert from closing to opening positions because the frozen positions have already been taken by others. They need to convert from closing positions to opening positions. And our expected result is that at this step, A's position has already changed to 5 long units. Plus these 3 units converted from closed to open positions, the expected result is a long position of 8 contracts. Regarding the transactional processing details during settlement for the previous 2 test cases, I have provided a detailed explanation in other videos about distributed transactions. I haven't gone into as much detail here, so if you want to understand the details, you can watch the video on distributed inputs. Okay, the last scenario is actually the same as the second one. So where's the difference? The difference is that at the start of the second test, A is holding a short position. And at the start of this test, A's status is a long position. It's just testing resource contention in concurrent errors in both directions, just changing the direction of the test. And the content of the test follows the same logic. And finally, the other scenarios below are all based on the first scenario with some slight modifications. In the first scenario above, A is always in a long position. He first buys and then reduces, increases, or closes the position while in a long position. Then, yes, it verifies opening, reducing, and closing positions while in a long position. In the second scenario, it's the reverse, a short position scenario where all buys and sells are reversed. A initially sells 5 units, resulting in 5 short units, and then proceeds with closing or increasing the position. Then the test for completely closing the position and the flip test. That's the difference between 1 and 2, setting expectations for long and short positions. Okay. And for scenario 3, it's exactly the same as scenario 1, except that A switches from being the maker to the taker in all transactions. And for scenario 4, it's exactly the same as scenario 2, except A acts as the taker. Okay. Then the fifth one is exactly the same as the first scenario, except B's order execution is split into 3 parts. And the sixth one is exactly the same as 2, except A's order execution is split into 3 parts to cover multiple order executions. As for 7 and 8, they refer to 3 and 4. After switching to take, the counterparty also breaks it down into 3B. And the very last one refers to number 1, just the one with BB. B has 3 single transactions, but those 3 transactions have amounts greater than, equal to, or less than A's order amount. Then for 10, it's the same, just refer to 2. And then we should add 2 more, which refer to 3. Follow reference 3. That's the reference. Let me see. 3 and 4. 5,678 already has this scenario, so it's not needed. Right, okay, that's fine. Okay, these are all our test cases. Now let's take a look at our automated integration test code. This code is in the Exchange test module under service in this project's change directory, where there is a test called trade test. I'll briefly explain this test. I won't go into too much detail. What does this test do? It initially sets up by first setting the host, then resetting all the user data. This means that all your user data will remain intact, but all transaction data and any user operation records like Kafka will be reset, only retaining the user data. Okay. After the reset, all database tables related to user operations will be reset, including the path and account information. After that, 3 accounts will be logged in, user A, B, and C, leaving tokens and then recharging these 3 users. After recharging, it will perform some initialization tasks. Some front-end cases will be read out, which will be used in the upcoming tests. Okay, this is actually what we do in the initial setup. All right, then we begin the testing. So what does this test do? This test will examine that. Let me check just now. This test will examine the part we just mentioned in scenario 1. I just did scenario 1 because once I complete scenario 1, it can cover the vast majority. The others are just some logical branches. And since this is an open source project, I didn't do them. I focused on making sure that a main branch is mostly correct. So I only test this part. So this test is to examine this. And here it tests A, the first number 1, A buys 5, B sells 5, A buys 5, B sells 5, expecting a long position of 5. The second is to test closing part of the position. Reducing position, the third is to test increasing the position, and then to test fully closing the position. And finally, when testing the flip project, a note for flip here is that the code on this side, the risk control side, has restrictions. In the code, let me find it. When users place an order, this will actually first check the user's position status in the position service, and if it would lead to a flip. It will be blocked because the flip situation only requires those compensation logics if it occurs after actual settlement. When users place orders, we aim to block these flips as much as possible to avoid compensation operations. So if a user really wants to reverse the position, they should first close the position completely themselves. Then place a reverse opening order themselves, requiring 2 separate orders to operate. So here, the risk control will block it. If the user doesn't split into 2 orders and just one order leads to a flip, it will be blocked. To test the flip scenario, this logic needs to be annotated out so that the orders causing a flip during placement won't be blocked. Okay, after annotation, we can start testing these three flip states. Then the method within each test, once you click in, actually follows the same logic. After setting the price and quantity, A and B respectively place orders. Users submit orders separately. Then you'll enter the expected position result here, what the expected value should be, and then verify it. User A accesses the API for their own position. To determine if it matches the expected value, then verify if user A's position status also matches the expected value. Yes, so you can set breakpoints here, and as you run the test, you can step through it and check the position data here while running. Check each one to see if the values you calculate based on the data here are exactly the same as my expected values. If they match exactly, it means the test is okay. You can look at each scenario together one by one. The main point is that at the end, the results for these three position summaries must match my expected values exactly. These can each be verified individually. Then the part about the actual position. And for the account part, check here if the spot assets are correctly deducted as margin when opening a position. Then the margin is moved to the main position margin, and fees are all calculated correctly. Yes, and then set breakpoints and proceed step by step, one by one. Okay, I've verified this thoroughly. And just to add, because Kafka transactions and search engines send events asynchronously, there will be some delays. So in each order action during testing, there's a pause, a sleep, pausing for a few seconds before proceeding to the next step. Each order action will do this. If you find that the test fails after placing an order, there are two possible reasons. The first is that your machine is running many services and clusters, resulting in higher latency. You should increase these delay times a bit. The second reason might be that the test didn't pass because after placing an order, the order status remains in the frozen margin state, not moving to the new state and not entering matching. This is because the Kafka connects subscribe to the MySec bin log. The connector that subscribes to the bin log to send events to the topic is malfunctioning. In this case, click Reset Data and it will reset. I've already implemented some actions inside and it will automatically reset the Kafka connector for you. The process of subscribing to the bin log. If resetting doesn't work, you might need to use this here. In K8s, the Kafka connectors have an HTTP script with several HTTP requests to check its status. And if the status is wrong, you delete it. After deleting the subscription task, rebuild it. And if you encounter issues, consult AI.